Out there in the vast emptiness of space, where distances are measured in billions of light years and time stretches beyond human comprehension, a single, nearly weightless traveler was silently carrying a secret. It had journeyed across the cosmos, untouched and unseen, until one extraordinary moment when it crashed into a detector buried deep beneath the ice of Antarctica. This wasn't just any particle, this was a neutrino, and it held evidence of a crime seen on an intergalactic scale. Picture this, a cataclysmic explosion so powerful it could tear apart stars, hidden billions of years ago in a distant corner of the universe. And yet, its story reached us, carried by this one tiny messenger. What makes this discovery so astonishing isn't just the scale of the event, it's the sheer improbability that we could ever find it. Neutrinos are famously elusive, passing through entire planets like ghosts. Trillions stream through your body every second, leaving no trace. So how did scientists manage to catch this one? And more importantly, how did they trace it back to a violent, ancient explosion in a galaxy far beyond our own? The answer is a story of cosmic detective work, cutting-edge technology, and a bit of luck, one that rewrites what we thought we knew about the universe's most extreme events. This is more than just a tale of scientific discovery. It's a glimpse into how the universe talks to us, sending signals in ways we're only beginning to understand. That single neutrino wasn't just a random speck in the dark. It was a clue pointing to something far grander. And as we follow its trail, we'll uncover how scientists pieced together the evidence, what it reveals about the hidden forces shaping our cosmos, and why this tiny particle might hold the key to unlocking even greater mysteries. So buckle up, we're about to dive into one of the most thrilling space detective stories ever told. Neutrinos are the universe's ultimate escape artists, so small and slippery that they barely interact with anything at all. To put it in perspective, a neutrino could fly through a block of lead a light year thick and still have a good chance of making it out the other side untouched. That's why detecting one is like trying to catch smoke with your bare hands. But this very elusiveness is what makes them invaluable. While light from distant cosmic explosions can be blocked or distorted by dust, gas, or magnetic fields, neutrinos zip straight through, carrying pristine information from the most violent events in the universe. For decades, scientists have built massive, ingenious detectors to catch these spectral particles, submerging them in deep mines, Antarctic ice, or even underwater. The goal: to capture the rare moment a neutrino finally bumps into an atom, releasing a faint but telltale signal. And in 2017, that patience paid off in a way no one expected. A single high-energy neutrino, detected by the IceCube observatory buried in the South Pole's ice, didn't just make a splash, it sent scientists racing to telescopes worldwide. Because this wasn't just any neutrino, its energy was off the charts, suggesting it came from something catastrophic. And when researchers traced its path back to the sky, they found something extraordinary: a flaring blazar, a supermassive black hole devouring material in a galaxy 4 billion light-years away. This was the first time a neutrino had ever been linked directly to a specific cosmic source, opening a whole new window into the universe. Before this, high-energy neutrinos were like random phone calls with no caller ID, frustratingly impossible to trace. But now we had proof they could act as cosmic breadcrumbs, leading us straight to the scene of the crime. And what a crime it was: a black hole hurling particles across the cosmos at nearly the speed of light, creating shockwaves powerful enough to shred matter. The implications were staggering. Neutrinos weren't just silent passers-by. They were witnesses carrying secrets from places light could never reach. And if we could learn to read their testimony, we might finally unlock the mysteries of the universe's most extreme environments. The moment scientists analyzed that peculiar neutrino's energy signature, they knew they were dealing with something extraordinary. Most neutrinos detected on Earth come from relatively mundane sources, our Sun, or cosmic rays interacting with the atmosphere. But this one packed a punch equivalent to a baseball traveling at 90 miles per hour, condensed into a particle a billion times smaller. That kind of energy doesn't just happen. It's the calling card of cosmic violence, a supermassive black hole tearing apart a star, or perhaps two neutron stars colliding in a cataclysm so bright it outshines entire galaxies. Tracking its origin required an unprecedented collaboration. As soon as IceCube flagged the neutrino's detection, telescopes across the globe swiveled to pinpoint its source. Like detectives combing through security footage, astronomers scoured archival data, and there it was. A Blazar, designated TXS 0506 plus 056, was in the midst of an explosive outburst. Nestled in the constellation Orion, 4 billion light-years away, this monster black hole had launched a jet of particles directly toward Earth, acting like a cosmic particle accelerator. The timing was uncanny. Just weeks before the neutrino arrived, the Blazar had begun flaring violently, its brightness surging to 15 times its normal level. But here's where the mystery deepens. While Blazars are known to emit light and gamma rays, no one had ever definitively tied them to high-energy neutrinos before. The discovery shattered assumptions. Neutrinos shouldn't easily escape such environments. Their production requires perfect conditions where protons smash together at near light speeds. Yet this one did, suggesting black hole jets might be far more efficient particle factories than anyone imagined. Even more intriguing, the neutrino arrived alone. Statistically, there should have been a shower of them. Its solitude implies something fundamental about how these extreme environments operate, possibly filtering particles in ways we don't yet understand. What makes this cosmic crime scene so compelling isn't just the violence, it's the precision of the evidence. For the first time, astrophysicists could directly connect a neutrino to a specific celestial object, like matching a fingerprint to a suspect. That Blazar's jet didn't just hurl light and radiation into the void. It fired a single, nearly massless bullet across 4 billion years, right into humanity's detectors. And in doing so, it revealed a universe far more interconnected and far stranger than we ever dreamed. Buried beneath the endless ice of Antarctica lies one of humanity's most extraordinary scientific instruments, IceCube, a neutrino observatory unlike any other. Imagine a grid of over 5,000 basketball-sized sensors, frozen solid in a cubic kilometer of pristine ice, waiting patiently for the rarest of interactions. This isn't just a detector, it's a trap designed to catch ghosts. Neutrinos barely interact with matter, but when they do, they leave behind an unmistakable signature, a faint burst of blue light called Cherenkov radiation. Picture a cosmic bullet striking the ice at nearly the speed of light, creating a shockwave of light that ripples outward. IceCube's sensors are tuned to catch that fleeting glow, transforming it into data scientists can analyze. But here's the catch. For every million neutrinos that pass through the detector, maybe, just maybe, one will collide with an atom and reveal itself. Building this frozen behemoth was a feat of engineering bordering on madness. Teams drilled 86 holes into the Antarctic ice, each 2.5 kilometers deep, then lowered strings of sensors into the abyss. The ice itself acts as both a shield and a medium, blocking out interference from cosmic rays while amplifying those precious neutrino signals. And it's not just about scale, it's about precision. IceCube sensors can pinpoint the direction of a neutrino's arrival to within less than a degree, allowing astronomers to trace its path back to a specific point in the sky. That's how, in September 2017, IceCube spotted something unusual, a neutrino with energy levels so high, it stood out like a flare in the dark. Scientists immediately alerted observatories worldwide, triggering a coordinated hunt across the electromagnetic spectrum. This wasn't just luck, it was the culmination of decades of planning, proving that even the universe's most elusive particles can't hide forever. What makes IceCube revolutionary isn't just its ability to detect neutrinos, it's how it turns them into cosmic messengers. Before this observatory, high-energy neutrinos were little more than theoretical curiosities. Now they're a new form of astronomy, revealing hidden corners of the universe that light alone could never illuminate. And as IceCube continues to listen to the whispers of these ghostly particles, who knows what other cosmic crimes it might uncover. Tracing the path of that single neutrino was like following a single drop of water back to a storm raging halfway across the universe. The moment IceCube detected the particle's faint blue flash, astronomers knew they had a cosmic mystery on their hands, one that required more than just a single instrument to solve. Think of it like this: if the neutrino was a bullet, IceCube could tell us the direction it came from, but not who fired the gun. To crack the case, scientists needed eyes everywhere, telescopes scanning the skies in every wavelength, from radio waves to gamma rays. The breakthrough came when they cross-referenced IceCube's data with observations from the Fermi Gamma Ray Space Telescope. Hidden in the noise was a Blazar, a galaxy with a supermassive black hole at its core, spewing out a jet of particles pointed directly at Earth. This wasn't just a lucky guess, the alignment had to be precise. Neutrinos travel in near-perfect straight lines, barely swayed by magnetic fields or other cosmic obstacles. That meant the Blazar had to be almost exactly along the same line as the neutrino's path. And there it was, TXS 0506 plus 056, a name as unassuming as its location in a quiet patch of Orion. But this galaxy was anything but quiet. What made this discovery so groundbreaking wasn't just the distance. 4 billion light-years is staggering, but not unheard of in astronomy. It was the nature of the source itself. Blazars are some of the most extreme environments in the universe, where black holes spin like frenzied tops, whipping particles to near light speeds and launching them across the cosmos. But until this moment, no one had definitive proof that these monsters could produce high-energy neutrinos. The implications were huge. If Blazars were neutrino factories, it meant their jets could accelerate particles in ways we hadn't fully understood, creating conditions so violent they could shred matter into its most elusive fragments. Yet the real surprise was how clean the evidence was. Usually, cosmic detective work involves sifting through layers of interference, like trying to hear a whisper in a crowded room. But this neutrino arrived with a clarity that felt almost deliberate. It wasn't part of a diffuse shower of particles. It was a solitary messenger carrying a story from deep inside that jet. That uniqueness is what makes it so valuable. Most high-energy events in the universe send out a chaotic mix of signals, but this one handed scientists a single, pristine clue. And as they pieced together the timeline, something even more intriguing emerged. The Blazar had been flaring wildly just weeks before the neutrino's arrival. It was as if the universe had left a trail of breadcrumbs leading straight to the scene of the crime. Now the question is, what does this mean for our understanding of the cosmos? For starters, it proves that neutrinos can act as cosmic homing beacons, guiding us to events that might otherwise stay hidden. Light can be blocked or scattered, but neutrinos slip through everything, carrying unfiltered information from the universe's most chaotic corners. And if blazars are producing these particles, it suggests there's a whole layer of physics happening in those jets' processes we're only beginning to glimpse. This isn't just about solving one mystery, it's about opening a new window into the universe, one where neutrinos light up the darkness like flares in the void. To understand how a blazar could fire off a neutrino powerful enough to reach Earth from 4 billion light-years away, we need to dive into the chaos unfolding at its core. Picture a supermassive black hole millions of times heavier than our Sun, spinning like a whirlpool as it devours everything in its path. But this isn't just destruction, it's creation. As matter spirals inward, some of it escapes in the form of twin jets, blasted outward at nearly the speed of light. And if one of those jets happens to be aimed straight at us, we call it a blazar, a cosmic lighthouse with a beam so intense it outshines entire galaxies. Inside those jets, particles are accelerated to energies that dwarf anything we could produce on Earth. Protons, electrons, and other charged particles ricochet off magnetic fields, gaining speed with each pass until they're traveling at a fraction below light speed. But here's where things get interesting. When these ultra-fast protons collide with photons or other particles, they can spawn something fleeting yet powerful pions, which decay almost instantly into neutrinos and gamma rays. That's the smoking gun. The neutrino detected by IceCube was likely born in one of these violent collisions, a byproduct of protons smashing together with so much force that they shattered into fragments, including this ghostly messenger. The real puzzle, though, isn't just how the neutrino was made, it's how it escaped. Blazar jets are turbulent environments, filled with magnetic fields and swirling plasma that should trap or deflect particles. Yet this neutrino slipped through, untouched, as if the chaos around it simply parted ways. That suggests something extraordinary. These jets might have escape routes, regions where conditions align just right to let high-energy particles punch through. It's like a cosmic version of threading a needle, except the needle is a tunnel through a storm, and the thread is a particle smaller than an atom, traveling across the universe without a single misstep. What's even more remarkable is the timing. The blazar was in the middle of a violent outburst when the neutrino arrived, as if the black hole had turned up its dial to maximum. That flare likely created the perfect conditions for neutrino production, a surge of particles colliding at unprecedented energies. And while we've seen blazars flare before, this was the first time we caught one in the act of sending us a neutrino. It's like stumbling upon a fingerprint at a crime scene, then realizing the suspect left a signed confession right next to it. This discovery doesn't just solve one mystery, it opens a dozen more. If blazars can produce neutrinos this energetic, what else might their jets be hiding? Could there be other, even more extreme processes at work, ones we haven't even imagined yet? And with IceCube and other detectors now on high alert, how many more of these cosmic messengers are out there, waiting to point us toward the universe's next great enigma? Every neutrino is a story, and this one just handed us the first chapter. Blazars don't just fling particles into space, they're cosmic demolition derbies where matter gets torn apart and rebuilt with energies that make our most powerful particle colliders look like toys. At the Large Hadron Collider here on Earth, we smash protons together at nearly the speed of light to study the fundamental building blocks of the universe. But a blazar's jet, it does the same thing on a scale we can barely comprehend, with energies millions of times higher. Take the blazar that sent us that fateful neutrino. Its jet isn't just a stream of particles, it's a chaotic, hyperactive zone where protons get whipped around by magnetic fields, gaining speed until they collide with photons or other particles. These crashes are so violent, they don't just produce neutrinos, they create entire particle showers like sparks flying from a grinding wheel. It's in these collisions that something extraordinary happens. Protons transform. They shatter into pions, which then decay almost instantly, spitting out neutrinos as their final act. This process solves a puzzle that's baffled scientists for decades. High-energy neutrinos have been detected before, but their origins were a mystery. Some theories pointed to blazars, but without direct evidence. It was like trying to prove a suspect was at a crime scene without fingerprints. That single neutrino changed everything. Its energy matched predictions perfectly, confirming blazars as neutrino factories. And not just any factories, these are cosmic supercolliders, operating on scales and energies we can't replicate, showing us physics in its most extreme form. What's even wilder is how efficient these natural accelerators are. While our colliders on Earth require massive infrastructure, miles of tunnels, supercooled magnets, and enough electricity to power a city, blazars do it effortlessly, powered by nothing more than gravity and chaos. A supermassive black hole's pull twists spacetime itself, creating conditions so extreme that particles get ejected with pinpoint precision across billions of light years. And that neutrino, it's proof that these jets don't just spew energy randomly, they focus it like a cosmic sniper rifle firing particles across the universe. But here's the twist, not all blazars may be capable of this. The one that produced our neutrino was in a rare flaring state, meaning it was especially active. That suggests these events might be episodic windows of opportunity where conditions align just right for neutrino production. It's like catching a volcano mid-eruption. Most of the time, it smolders, but when it blows, it sends material flying farther than you'd think possible. This discovery doesn't just fill in a gap in our understanding, it opens a new frontier. If blazars can produce neutrinos this energetic, what else might their jets be hiding? Could there be even more exotic particles or processes we haven't yet imagined? And with each new neutrino we detect, we're not just collecting data, we're piecing together the operating manual of the universe's most powerful engines. Magnetic fields are the invisible architects of chaos within a blazar's jet, thread-like forces that twist, snap, and whip particles to unimaginable speeds. Without them, that high-energy neutrino might never have reached us. Picture a cosmic slingshot. As charged particles spiral along these magnetic field lines, they gain energy with each loop, like a roller coaster climbing higher and higher before finally being hurled outward. But here's the twist. These fields don't just accelerate particles, they also act as cosmic colliders, smashing them together with enough force to shatter protons into neutrinos and other exotic fragments. The process starts deep in the blazar's heart, where the supermassive black hole's rotation winds up magnetic fields like coiled springs. These fields channel the jet's particles into tight, spiraling paths, forcing them to interact in ways that wouldn't happen otherwise. When two protons collide under these extreme conditions, they don't just bounce off each other, they explode into a shower of secondary particles, including pions. And as those pions decay, they release the universe's most elusive travelers, neutrinos. What's astonishing is the precision of this chaos. The magnetic fields don't just randomize the particles, they focus their energy, ensuring some neutrinos escape the jet's turbulence in a straight line, like a bullet fired through a hurricane. Scientists once thought these magnetic fields would scramble any outgoing particles, making it impossible to trace neutrinos back to their source. But the detection of that single high-energy neutrino proved otherwise. Its path was so straight, so undisturbed, that it hinted at something unexpected. Pockets of order within the blazar's jet where magnetic fields align just right to let particles slip through unscathed. It's as if the universe left a door ajar, allowing one ghostly messenger to escape with its story intact. This discovery reshapes our understanding of cosmic accelerators. Before, magnetic fields were seen as chaotic disruptors, but now we know they're also enablers, fine-tuning particle collisions to produce neutrinos with pinpoint efficiency. And if blazars can do this, what about other extreme environments? Could supernova remnants or merging neutron stars also harbor these hidden zones of order? The answers might be hiding in the next neutrino that streaks through IceCube, carrying secrets from the universe's most violent workshops. One thing's certain: magnetic fields aren't just background players in the cosmos. They're the conductors of an invisible symphony, orchestrating the birth of particles we're only beginning to understand. For centuries, astronomers relied on just one tool to study the universe: light. Telescopes captured the glow of stars, the shimmer of galaxies, and the flicker of distant explosions, but light alone could only tell part of the story. Imagine trying to solve a murder case with only a single blurry photo from the crime scene. You might spot the weapon, but without fingerprints, witness testimonies, or security footage, crucial details would stay hidden. That's why the detection of that single neutrino wasn't just a breakthrough, it was a revolution. For the first time, scientists could combine its data with observations from telescopes across the electromagnetic spectrum, creating a complete, multi-dimensional picture of the blazar's violence. This is the power of multi-messenger astronomy, turning cosmic whispers into a chorus. The blazar's outburst wasn't just a flare of visible light or gamma rays. It was a symphony of signals, each carrying a different piece of the puzzle. Gamma rays revealed the raw energy of particles in the jet, while radio waves traced the jet's sprawling structure across space. X-rays exposed the scorching temperatures near the black hole, and optical telescopes captured the flickering glow of matter spiraling toward oblivion. But without the neutrino, scientists might never have confirmed the blazar as the culprit. Think of it like matching a suspect's DNA to blood found at the scene. While light can be blocked or scattered, neutrinos barrel straight through the universe untouched, carrying unimpeachable evidence from the heart of the chaos. This collaborative approach is reshaping astrophysics. When gravitational waves from colliding neutron stars were detected in 2017, telescopes worldwide swiveled to catch the afterglow, a flash of light called a kilonova. That event proved gravitational waves and light could work together to reveal cosmic secrets. Now, with neutrinos in the mix, we've added another voice to the conversation. Each messenger brings something unique. Light shows us where things are, gravitational waves tell us how they move, and neutrinos expose what's happening inside the most extreme environments. Together, they're like witnesses describing the same crime from different angles. One saw the getaway car, another heard the gunshot, and a third caught the license plate. What makes this era so thrilling isn't just the technology, it's the sheer unpredictability of what we might discover next. Before multi-messenger astronomy, high-energy neutrinos were ghosts in the data, impossible to trace. Now they're guideposts pointing to hidden corners of the universe where black holes shred stars and galaxies collide. And as detectors grow more sensitive, with projects like the upcoming cubic-kilometer neutrino telescope expanding our reach, we're on the verge of catching even fainter signals, perhaps from events we haven't even imagined yet. The Blazar's neutrino was a starting pistol. The race to decode the universe's full story has only just begun. While IceCube was the first to catch that fateful neutrino, it was the Fermi Gamma Ray Space Telescope that helped seal the case. Orbiting high above Earth's atmosphere since 2008, Fermi scans the skies for gamma rays, the most energetic form of light, often born in the universe's most violent events. And when scientists checked its data, they found something extraordinary. A flare of gamma rays bursting from the exact same patch of sky as the neutrino's origin. This wasn't a coincidence, it was confirmation. Gamma rays and neutrinos are like two sides of the same cosmic coin. In the chaos of a Blazar's jet, when protons collide at near light speeds, they don't just produce neutrinos, they also generate gamma rays. So when Fermi spotted that sudden spike in radiation, it was like finding a second fingerprint at the crime scene. The timing was critical. The gamma-ray flare peaked just weeks before the neutrino arrived, suggesting the Blazar's jet had entered a hyperactive state, churning out particles with unprecedented intensity. Without Fermi's eyes on the sky, the neutrino might have remained a tantalizing mystery. Instead, the two signals together painted an undeniable picture. This Blazar wasn't just brightening, it was firing bullets of matter and light across the universe. What makes this partnership between IceCube and Fermi so groundbreaking is how they complement each other. IceCube hunts particles that barely interact with matter, while Fermi captures light that's easily absorbed by Earth's atmosphere. One reveals the hidden, the other the visible. Together, they form a complete toolkit for probing the cosmos. It's like pairing a detective who specializes in fingerprints with one who analyzes security footage. The combined evidence is far stronger than either could provide alone. But Fermi's role didn't stop there. By monitoring the Blazar's gamma-ray output over time, it helped scientists reconstruct the chain of events leading up to the neutrino's escape. The data revealed how the jet's activity spiked and faded, offering clues about the conditions that allowed such a high-energy particle to break free. This wasn't just about solving a single mystery, it was about learning how Blazars behave during their most violent episodes and how often they might send similar messengers our way. The success of this collaboration hints at a future where space exploration isn't just about building bigger telescopes, but smarter networks. Imagine a global alert system where detectors like IceCube, Fermi, and gravitational wave observatories automatically share data, triggering rapid follow-up observations whenever something unusual occurs. We're already seeing glimpses of this with events like the neutron star collision detected in 2017, where telescopes worldwide raced to capture the aftermath. The Blazar neutrino proved that neutrinos belong in this new era of multi-messenger astronomy, not as outliers, but as essential voices in the cosmic chorus. And that's the real takeaway here. No single instrument, no matter how advanced, can unravel the universe's secrets alone. It's the combination of perspectives. The neutrinos whisper, the gamma rays flash, the gravitational waves ripple, that transforms fragments of data into a story. The Blazar didn't just give us a neutrino, it handed us a blueprint for how to explore the invisible forces shaping our universe. And with every new detection, we're not just collecting dots, we're learning how to connect them. That single neutrino didn't just solve a mystery, it ignited a revolution. For decades, neutrino astronomy was a field built on hope and theory, with scientists straining to catch particles so elusive they seemed almost mythical. But in 2017, everything changed. The detection of that high-energy messenger from a distant Blazar didn't just validate decades of work, it flung open a door to an entirely new way of exploring the cosmos. Suddenly, neutrinos weren't just curiosities, they were tools, cosmic telegrams from places light could never reach. Think of it like this: before this discovery, studying the universe was like trying to understand a thunderstorm by only looking at the lightning. You'd see the flash but miss the rumble of the thunder, the shift in air pressure, the way the wind howls before the rain. Neutrinos are that missing data, the rumble, the shift, the hidden signals that complete the picture. With them, scientists can peer inside celestial furnaces like Blazar jets, supernova remnants, and colliding neutron stars, places where matter is shredded and rebuilt under conditions we can't replicate on Earth. The implications stretch far beyond a single blazar. Neutrino astronomy lets us test theories about the universe's most extreme physics, like how black holes accelerate particles to near light speeds, or whether dark matter might decay into neutrinos we could detect. It's a field where every new observation has the potential to rewrite textbooks. Take cosmic rays, for example. These high-energy particles bombard Earth from deep space, but their origins have been debated for over a century. Now, with neutrinos as tracers, we might finally pinpoint the cosmic factories that produce them. What makes this breakthrough so transformative isn't just the science, it's the collaboration. IceCube's success hinged on a global network of telescopes, from radio dishes in Chile to gamma-ray detectors in orbit, all working in unison. This wasn't a solo effort. It was a symphony of technology, with each instrument playing a vital role. And the best part, we're just getting started. Upcoming projects like the cubic kilometer neutrino telescope in the Mediterranean aim to expand our reach, while next-generation detectors could one day catch neutrinos from the earliest moments of the universe. The Blazar's neutrino was more than a particle, it was a proof of concept. It showed that the universe speaks in more than just light, and if we learn to listen, the secrets it reveals could be staggering. Every time a neutrino streaks through a detector now, it's not just a blip on a screen, it's a message waiting to be decoded. And somewhere out there, in the darkness between galaxies, another one might already be on its way, carrying clues to mysteries we haven't even thought to ask about yet. Black holes aren't just cosmic vacuum cleaners, they're the ultimate particle accelerators, operating on scales that dwarf anything humans could ever build. Take that Blazar's supermassive black hole, for example. Its jet wasn't just hurling matter into space, it was a natural laboratory, recreating conditions so extreme they defy the laws of physics as we know them. While the Large Hadron Collider smashes particles together at energies of around 13 trillion electron volts, this Blazar's jet was flinging protons with energies 1,000,000 times higher. That's like comparing a firecracker to a supernova. What makes these environments so unique isn't just the raw power, it's the way they warp the very fabric of reality. Near a black hole's event horizon, gravity is so intense that space and time twist like taffy. Magnetic fields, stronger than anything in our solar system, whip particles to near light speed in milliseconds. And in that chaos, something extraordinary happens. Matter gets torn apart and reassembled in ways we've only theorized. The neutrino IceCube detected was a byproduct of this mayhem, a single shred of evidence from a place where protons collide with enough force to shatter into particles we can barely detect, let alone understand. This isn't just academic curiosity. Studying these cosmic laboratories lets scientists test theories that would otherwise remain untouchable. For instance, Einstein's theory of general relativity predicts how black holes bend space-time, but the extreme physics inside their jets might reveal where those rules break down. Some theories suggest that at these energies, unknown particles or forces could emerge, ones that don't exist in our tame, low-energy universe. It's like having a microscope that only works if you're staring into the heart of a hurricane. And then there's the puzzle of acceleration. On Earth, we need miles of tunnels and gigawatts of power to push particles to high speeds. But black holes do it effortlessly, using nothing but gravity and magnetism. How? That's still a mystery. One leading idea involves magnetic reconnection, a process where tangled field lines snap like rubber bands, releasing bursts of energy that launch particles to unimaginable velocities. But without direct observations, it's all speculation. That's why neutrinos are so crucial. They're the only witnesses that can escape these environments and tell us what's really happening. What's even more mind-bending is the timescale. While human-built colliders produce collisions in controlled, nanoseconds-long bursts, Blazar jets sustain these reactions for centuries. They're not just labs, they're perpetual motion machines of particle physics, running experiments on galactic scales. And with each neutrino we catch, we're essentially peering over the shoulder of the universe as it conducts its most violent research. This Blazar wasn't just a curiosity, it was a Rosetta Stone for high-energy physics. By comparing its neutrino to data from Earth-based colliders, scientists can spot discrepancies that might hint at new physics. Maybe the neutrino's energy doesn't quite match predictions, suggesting an unknown particle in the decay chain. Or perhaps the jet structure reveals flaws in our models of magnetic acceleration. Every anomaly is a clue pointing toward gaps in our understanding. The irony is delicious. Black holes, famous for devouring information, might be the very things that help us uncover it. They take the rulebook of physics and shred it, leaving us to piece together a new one from the fragments. And with each neutrino that streaks through our detectors, we're not just solving a puzzle, we're rewriting the rules of the game. Detecting neutrinos is like trying to catch smoke with a fishing net. They slip through almost everything without leaving a trace. These ghostly particles are so indifferent to matter that they can pass through a light year's worth of solid lead without a single interaction. That's why hunting them demands more than just precision. It requires sheer scale. Enter IceCube, a detector so massive it spans an entire cubic kilometer of Antarctic ice. But even with that size, it only catches a handful of neutrinos each year. To understand just how rare these detections are, consider this. Trillions of neutrinos stream through your body every second, yet IceCube might register just a few hundred meaningful events annually. The reason lies in how neutrinos interact, or rather how they don't. Unlike charged particles which bump into atoms constantly, neutrinos only respond to the weak nuclear force, one of the universe's most feeble influences. For a neutrino to finally announce its presence, it must strike an atomic nucleus dead-on, an event so unlikely it borders on miraculous. When it does happen, the collision releases a faint burst of blue light Cherenkov radiation, which IceCube's sensors can pick up. But even then, there's a catch. The ice must be flawlessly clear, free of bubbles or impurities that could scatter the light and obscure the neutrino's path. That's why Antarctica's ancient, densely packed ice is the perfect medium. It's nature's own ultra-pure detector. Building IceCube was an engineering feat akin to threading a needle across a continent. Teams drilled holes 2.5 kilometers deep into the ice, then lowered strings of sensors into the abyss, where temperatures hover at -50 degrees Celsius. Each sensor had to withstand crushing pressure and extreme cold while remaining sensitive enough to catch that fleeting blue glow. And the data, it's a deluge. IceCube processes thousands of false signals daily: cosmic rays, atmospheric neutrinos, even random noise from the ice itself. Finding a single high-energy neutrino from deep space is like spotting one unique grain of sand on a beach. Yet every detection is worth the effort. Unlike light, which can be absorbed or bent by cosmic obstacles, neutrinos travel straight from their source, carrying unaltered information about the violent events that created them. When IceCube caught that Blazar's neutrino, it wasn't just luck. It was the culmination of decades of innovation, proving that even the universe's shyest particles can't hide forever. The challenge now, scaling up. Next-generation detectors, like the proposed cubic kilometer neutrino telescope, aim to expand our reach, turning these rare cosmic whispers into a chorus. Because in the hunt for neutrinos, every interaction is a window into the universe's best-kept secrets. Light might be the universe's most obvious storyteller, bright, vivid, and everywhere, but it's also notoriously unreliable. The second it leaves its source, it's at the mercy of everything in its path. Cosmic dust clouds scatter it, magnetic fields bend it, dense regions of space swallow it whole. By the time starlight reaches us, it's often distorted, dimmed, or completely erased, like a message smudged beyond recognition after passing through too many hands. But neutrinos, they don't just ignore these obstacles, they laugh at them. Picture a beam of light trying to escape a galaxy's core, where thick swirls of gas and dust choke its path. It might take thousands of years just to struggle free, its wavelengths stretched and scrambled. Now imagine a neutrino born in that same violent heart. In the time it takes you to blink, it's already streaking through the galaxy's outer edges, untouched. No dust grain slows it down, no magnetic field diverts its path. It's the ultimate cosmic bullet, piercing through walls that stop light dead in its tracks. This indifference to interference makes neutrinos more than just messengers. They're pristine records of events light could never faithfully report. Take the centers of active galaxies, where supermassive black holes churn matter into oblivion. Telescopes see these regions as hazy, glowing blobs, their details blurred by the very materials swirling around them. But neutrinos, they barrel straight out, carrying unfiltered snapshots of the chaos within. It's the difference between trying to photograph a raging fire through thick smoke and holding a perfectly clear sample of the flames themselves. The implications are staggering. Right now, there are corners of the universe so shrouded in dust and plasma that they're effectively invisible to traditional astronomy. Yet somewhere in that darkness, neutrinos are streaming toward us, each one a potential eyewitness to events we've never seen. Some might come from the hearts of galaxies so distant, their light hasn't even reached us yet. Others could be relics of ancient collisions between neutron stars, their light long faded but their neutrino signals still fresh. But here's the real kicker. Neutrinos don't just complement light, they correct its blind spots. When a supernova explodes, the first signal to arrive isn't the flash of light. It's a burst of neutrinos, racing ahead by hours because they slip effortlessly through the star's outer layers while photons fight to escape. In 1987, detectors caught neutrinos from a dying star in the Large Magellanic Cloud, a full 3 hours before telescopes saw the explosion. That early warning proved neutrinos could act as cosmic alarm bells, giving us a heads up when the universe is about to do something spectacular. Of course, light still has its place. It reveals the colors, shapes, and motions of celestial objects in ways neutrinos never could. The two aren't rivals, they're partners, each telling a different part of the same story. But in the hunt for the universe's deepest secrets, neutrinos offer something priceless: clarity. Where light gets lost, they persist. Where photons scatter, they stay true. And as we learn to read their signals, we're not just adding another tool to astronomy's kit, we're opening a backdoor to the cosmos, one that leads straight to the scenes light can't reach. If you think IceCube is impressive, just wait until you see what's coming next. The success of catching that single high-energy neutrino didn't just prove the concept, it sparked a race to build detectors so advanced they'll make IceCube look like a first-generation telescope. Scientists are already designing observatories with 10 times the sensitivity, capable of catching neutrinos so faint they've been invisible until now. And the key: scale. Imagine a detector not just buried in ice, but submerged in the depths of the Mediterranean Sea or sprawled across the ocean floor, turning entire landscapes into cosmic listening devices. One of the most ambitious projects on the horizon is the Cubic Kilometer Neutrino Telescope, or KM3NT. Instead of Antarctic ice, it'll use the clear, dark waters of the Mediterranean as its detection medium. Thousands of optical sensors will dangle like pearls on strings, waiting for the telltale blue flashes of neutrino interactions. Why water? Unlike ice, which can scatter light, deep seawater offers near-perfect clarity, allowing detectors to track neutrinos with even sharper precision. And because KM3NT will span several cubic kilometers, it'll catch far more neutrinos, potentially hundreds per year, giving scientists a flood of data where they once had mere trickles. But it's not just about size. Next-gen detectors are getting smarter too. Advances in AI and machine learning let researchers sift through mountains of noise to find the faintest neutrino signals, like picking out a whisper in a hurricane. Some designs even incorporate holographic imaging to reconstruct neutrino interactions in 3D, revealing details about their energy and direction that were previously guesswork. And then there's P1, a proposed Pacific Ocean observatory that could leverage the ocean's vastness to create the largest neutrino detector yet, one that might finally catch neutrinos from the universe's earliest moments. The goal isn't just more detections, it's better ones. Future observatories aim to pinpoint neutrino origins with such accuracy that they'll rival optical telescopes. Picture this: a neutrino arrives and within minutes, telescopes worldwide swing into action, zooming in on a distant galaxy with surgical precision. That level of coordination could transform neutrino astronomy from a niche field into a cornerstone of astrophysics, letting us map the universe's most violent events in real time. What's truly thrilling, though, isn't just the technology, it's the potential discoveries. Fainter neutrinos could come from sources we've never seen: primordial black holes, dark matter annihilations, or even relics from the Big Bang. Some theories suggest that ultra-high-energy neutrinos might reveal cracks in our understanding of physics, hinting at dimensions or particles beyond the standard model. And with detectors like KM3NT and P1 coming online in the next decade, we're not just building better tools, we're writing the next chapter in the story of the universe, one neutrino at a time. Every answer in science seems to spawn 10 new questions, and this neutrino's journey is no exception. Sure, we've traced it back to a flaring blazar, but that's just the first clue in a much larger mystery. Why did this particular galaxy, among the countless others with supermassive black holes, suddenly fire off a particle with enough energy to cross 4 billion light-years and still punch through IceCube's detectors? Was it something special about the jet structure, a kink in the magnetic field, or a surge of infalling matter that created the perfect storm for neutrino production? Or is this blazar just one of many cosmic accelerators we haven't learned to recognize yet? The puzzle deepens when you consider how few neutrinos we've actually caught from this event. Statistically, a flare that violent should have sent a whole cascade of them our way. Yet only one made the trip. That anomaly suggests something fundamental about how these jets operate. Perhaps they're not the uniform particle factories we imagined, but more like cosmic volcanoes, erupting sporadically with bursts of energy that fling out single high-energy messengers. If that's true, it could rewrite our understanding of how black holes distribute their power, turning what we thought were steady streams into unpredictable geysers. Then there's the bigger question: what else is out there? Blazars can't be the only neutrino producers in the universe. Colliding neutron stars, supernova remnants, even the turbulent cores of galaxy clusters. All these environments have the raw energy to create high-energy particles. But so far, their neutrino signals have eluded us. Are we missing something fundamental about how these events operate? or have we just not built detectors sensitive enough to hear their whispers? The answer could reshape astronomy. If we discover that, say, merging neutron stars emit neutrinos in a pattern distinct from blazars, it would give us a whole new way to classify cosmic cataclysms not by their light, but by the hidden particles they emit. Perhaps the most tantalizing possibility is that we're on the verge of discovering entirely new neutrino sources. Some theorists speculate that dark matter, the invisible glue holding galaxies together, might decay into high-energy neutrinos we could detect. Others wonder if primordial black holes, relics from the Big Bang, could be lurking unseen, betraying their presence only through rare neutrino emissions. Even more exotic ideas float around, like cosmic strings, hypothetical defects in space-time vibrating enough to send neutrinos rippling across the cosmos. What's clear is that this field is just getting started. Every new neutrino detection is like finding a single page from a vast, scattered manuscript. We've pieced together enough to know the story is thrilling, but we're still missing entire chapters. The next generation of detectors, with their sharper eyes and broader reach, won't just add more pages, they might reveal entirely new plot twists. And somewhere in that data could be the answer to the biggest question of all. Are we seeing the universe's rulebook, or just the first draft? Before the Blazar discovery, supernova reigned as the undisputed champions of neutrino production. These stellar explosions were the stars, literally, of the neutrino world, famous for releasing such floods of these ghostly particles that detectors on Earth could pick them up from millions of light years away. When a star explodes, its collapsing core becomes a neutrino factory, squeezing protons and electrons together with such force that they merge into neutrons, releasing neutrinos as a byproduct. It's like squeezing a sponge until every last drop is forced out, except here, the sponge is a dying star, and the drops are trillions of nearly massless particles. For decades, supernovae were the only cosmic events definitively linked to neutrino bursts. The smoking gun came in 1987, when detectors caught neutrinos from a supernova in the Large Magellanic Cloud, a watershed moment that proved these particles could be cosmic messengers. That detection cemented supernova as the gold standard for neutrino astronomy. If you'd asked any astrophysicist back then where high-energy neutrinos came from, they'd have pointed to exploding stars without hesitation. But the Blazar discovery shattered that assumption. Suddenly, we had proof that another type of cosmic monster, supermassive black holes, could accelerate particles to energies even supernova couldn't match. The implications were staggering. If blazars could produce neutrinos, what else was out there? The universe, it seemed, had more than one way to make these elusive particles. This revelation didn't just add a new source to the list, it forced scientists to rethink the very nature of neutrino production. Supernovae create neutrinos through thermal processes, where extreme heat and pressure fuse particles together. Blazars, on the other hand, generate them through non-thermal mechanisms, flinging protons around like pinballs in a cosmic arcade until they smash into photons or other particles. That distinction matters because it means neutrinos can form in environments where scientists never thought to look. The fallout from this realization rippled through astrophysics. Models of cosmic particle acceleration had to be revised. Theories about the origins of high-energy cosmic rays long suspected to come from blazars gained new support. Even the search for dark matter felt the ripple effects as some researchers began wondering if neutrinos could help trace its invisible presence. Yet for all the excitement, supernovae haven't been dethroned. They're still neutrino powerhouses, and when the next nearby star explodes, detectors will be waiting. But now, they're no longer alone in the spotlight. The Blazar discovery revealed a universe far richer in neutrino sources than we'd imagined, one where black holes, neutron-star collisions, and who knows what else might be contributing to the cosmic neutrino background. It's as if we'd spent years studying rivers only to discover entire oceans hidden beneath the surface. What's next? That's the thrilling part. Every new neutrino detection could point to another unknown source, another piece of the puzzle. The hunt is on, and the rules have just gotten a lot more interesting. Neutrinos might be ghostly and nearly massless, but they could hold the key to unlocking one of cosmology's greatest mysteries: dark matter. This invisible substance outweighs all the stars, planets, and galaxies in the universe by a factor of 5, yet we've never directly observed it. It doesn't emit, absorb, or reflect light, hence the name dark, but its gravitational pull shapes the cosmos, bending the paths of galaxies and sculpting the large-scale structure of the universe. So how could something as tiny as a neutrino possibly be connected to something so vast? The answer lies in the gaps between what we know and what we've yet to discover. Most neutrinos we detect are low-energy particles from the sun or cosmic rays, but high-energy neutrinos like the one from that distant Blazar hint at processes far more extreme. Some theories suggest that dark matter particles, whatever they are, might occasionally decay or collide, producing high-energy neutrinos as a byproduct. If that's true, then every neutrino we catch could be more than just a messenger from black holes or supernovae. It might be a fingerprint left behind by dark matter itself. Of course, this is still speculative. Neutrinos as we know them are far too light to account for dark matter's gravitational heft. But what if they're not the whole story? Some models propose the existence of sterile neutrinos, a hypothetical, heavier cousin of the neutrinos we've detected. These particles would interact even less with ordinary matter, making them nearly impossible to spot except through their gravitational effects or the rare neutrino they might emit. It's a long shot, but if sterile neutrinos exist, they could solve two puzzles at once: the nature of dark matter and the origins of some high-energy neutrinos. The search for this connection is already underway. Experiments like IceCube aren't just hunting neutrinos from blazars. They're also scanning for unexplained neutrino bursts that could signal dark matter interactions. Imagine a neutrino arriving with no obvious source, no flaring galaxy, no nearby supernova. That anomaly might be the clue scientists need. Even more intriguing are proposals to study the neutrino fog from dense regions like the Milky Way's core, where dark matter is thought to cluster. If neutrinos from these areas show unexpected energy patterns, it could point to dark matter particles annihilating or decaying in the void. Skeptics argue that the link is tenuous at best. After all, we've spent decades searching for dark matter through countless other methods: underground detectors, particle colliders, even space telescopes, with no definitive results. Why should neutrinos be any different? But that's exactly what makes them so compelling. Unlike other dark matter hunters, neutrino observatories don't need the particles to interact directly with detectors. They just need to catch the aftermath, the faint blue glow of a collision that might have been triggered by something far stranger. Whether or not neutrinos ultimately reveal dark matter's secrets, the pursuit itself is reshaping astrophysics. Every high-energy neutrino we detect pushes the boundaries of what's possible, proving that even the universe's most elusive signals can't hide forever. And if one of them does turn out to be a cosmic telegram from dark matter, it would be like finding a single footnote in an ancient text, a small clue that unravels the entire story. Until then, the hunt continues, with each new detection bringing us closer to answers we're only beginning to imagine. This discovery wasn't just a win for scientists, it was a moment that electrified the public, proving that the universe's greatest mysteries aren't just solvable, but thrilling to unravel. When news broke that a single, nearly weightless particle had led astronomers to a violent black hole 4 billion light-years away, it wasn't confined to academic journals. Headlines lit up, social media buzzed, and suddenly terms like neutrino astronomy and multi-messenger astrophysics entered everyday conversations. People who'd never given particle physics a second thought found themselves captivated by the idea that invisible messengers from the cosmos could carry secrets across unimaginable distances. What made this story resonate wasn't just the science, it was the sheer drama of the hunt. The narrative had everything: an elusive particle, a cataclysmic explosion in deep space, and a globe-spanning collaboration of telescopes and detectors racing to piece together the clues. It transformed abstract physics into a cosmic detective story, one where the crime scene was a supermassive black hole and the smoking gun was a particle smaller than an atom. Museums and planetariums quickly incorporated the discovery into exhibits, using it to illustrate how modern astronomy blends cutting-edge technology with old-fashioned curiosity. Teachers seized on it as a way to make particle physics tangible, showing students that even the tiniest things can lead to the biggest revelations. Beyond inspiration, the breakthrough underscored something deeper: the value of investing in big, ambitious science. Projects like IceCube aren't cheap. They require years of funding, international cooperation, and infrastructure that pushes engineering to its limits. Critics sometimes dismiss these endeavors as impractical, asking why we'd bury sensors in Antarctic ice or launch telescopes into orbit when there are pressing problems on Earth. But this discovery was a perfect counterargument. Without IceCube's relentless pursuit of neutrinos, we'd have never known blazars could produce them, let alone traced one back to its source. And that knowledge isn't just academic. It's a stepping stone to understanding the universe's most energetic processes, which could one day revolutionize everything from energy production to materials science. The ripple effects extended far beyond astrophysics. The story highlighted how foundational research, the kind without immediate commercial payoff, often leads to the most transformative breakthroughs. GPS, Wi-Fi, even cancer treatments owe their existence to discoveries made by scientists following curiosity, not profit. When the public sees a neutrino pinpoint a black hole, it's a reminder that today's useless experiment might be tomorrow's paradigm shift. Funding agencies took note, using the discovery to advocate for sustained support of large-scale projects. Politicians cited it in speeches about the importance of basic research, and philanthropists redirected donations toward neutrino observatories, eager to be part of the next big revelation. Perhaps most importantly, the event demystified how science actually works. Unlike the Hollywood trope of a lone genius having a eureka moment, this was a story of collaboration of ice drillers in Antarctica, engineers in Wisconsin, and astronomers in Chile working in unison. It showed science as a collective, often messy endeavor where progress hinges on patience, teamwork, and the willingness to chase faint signals into the unknown. For aspiring scientists, that's a far more relatable and empowering message than the myth of solitary brilliance. The Blazar neutrino did more than advance astrophysics. It became a cultural touchstone, a proof of concept that the universe is stranger and more interconnected than we dared to imagine. And in an era where science is often politicized or dismissed, that's no small feat. It reminded us that curiosity isn't just a luxury. It's how we uncover truths that reshape our place in the cosmos. The next time a neutrino streaks through a detector, it won't just be scientists paying attention. The world will be watching, waiting to see what other secrets these ghostly particles might reveal. The hunt for that single neutrino wasn't just a triumph of technology, it was a testament to the power of human collaboration. Scientists from over 40 institutions across a dozen countries dropped everything the moment IceCube's alert went out, racing to confirm the discovery. Telescopes in Chile swiveled toward Orion. Gamma-ray detectors in orbit adjusted their focus. Researchers from Tokyo to Berlin pored over data, their collective expertise transforming a faint signal into a groundbreaking revelation. This wasn't just teamwork, it was a synchronized dance of global science, proving that the universe's biggest mysteries can't be solved alone. Consider the logistics. When that neutrino hit IceCube, astronomers had mere hours to act before Earth's rotation carried the Blazar out of view for key telescopes. Time zones became irrelevant. Sleep was sacrificed. Emails flew between continents at all hours as teams shared observations in real time, piecing together clues like a high-stakes jigsaw puzzle. The Fermi Gamma Ray Space Telescope, operated by NASA with international partners, played a pivotal role by confirming the Blazar's flare. Meanwhile, optical telescopes in the Canary Islands and Hawaii captured critical details about the jet structure, while radio arrays from Australia to Europe mapped its sprawling tendrils. Each dataset was a fragment of the truth, useless in isolation, but transformative when combined. What's remarkable isn't just the scale of cooperation, but how it reshaped science itself. Traditionally, astrophysics was siloed. Neutrino physicists, gamma-ray astronomers, and optical researchers often worked in parallel, rarely crossing disciplinary lines. This discovery shattered those barriers. Suddenly, particle physicists were deciphering telescope data, while astronomers found themselves knee-deep in neutrino interaction models. The collaboration even spilled into engineering, as teams improvised ways to recalibrate instruments on the fly, adapting to the neutrino's unexpected energy profile. It was a masterclass in intellectual flexibility, proving that breakthroughs happen when diverse minds converge on a single problem. The financial and cultural hurdles were just as daunting. IceCube's construction alone required funding from the U.S. National Science Foundation, Belgium, Germany, and Sweden, with maintenance supported by teams braving Antarctica's brutal winters. Meanwhile, telescopes like the Very Large Array in New Mexico, originally designed for entirely different research, were repurposed for neutrino follow-ups, a testament to scientific agility. Language barriers, software incompatibilities, and even conflicting time zones could have derailed the effort. Yet the shared goal overrode every obstacle, forging a blueprint for future discoveries. This model is now the gold standard. When gravitational waves rippled through detectors in 2015, the global astronomy community knew exactly how to respond because collaborations like the Blazar hunt had proven the value of readiness. Today, neutrino alerts trigger automated telescope networks worldwide, with AI streamlining data analysis across borders. The lesson is clear. In an era of cosmic detective work, no single instrument or nation holds all the clues. The next great breakthrough might depend on a grad student in Johannesburg spotting an anomaly, a programmer in Tokyo writing a critical algorithm, or a technician in Chile adjusting a lens at just the right moment. Together, they're not just studying the universe, they're redefining how we explore it. The story of that lone neutrino didn't just revolutionize astrophysics, it became a beacon for classrooms and lecture halls worldwide. Teachers seized on its detective story appeal, transforming abstract particle physics into something tangible. Imagine a high school science lab where students trace the path of a hypothetical neutrino through a makeshift IceCube, built from clear gelatin and LED lights, watching as their tiny blue flashes mimic Cherenkov radiation. or college astronomy courses using the Blazars flare to demonstrate multi-messenger astronomy, showing how combining neutrino data with gamma-ray observations paints a fuller picture than either could alone. This wasn't just a lesson, it was an invitation to join the hunt for cosmic secrets. Museums amplified the excitement with interactive exhibits that let visitors step into scientists' shoes. The Museum of Science in Boston created a simulation where guests could align virtual telescopes based on neutrino alerts, racing against a clock to pinpoint the source before Earth rotation carried it away. Meanwhile, the Deutsches Museum in Munich installed a towering model of IceCube's sensor grid, its lights flickering whenever real detectors picked up neutrinos, connecting visitors to live discoveries happening a continent away. These exhibits didn't dumb down the science, they made it visceral. One curator described overhearing a child whisper, "I want to catch neutrinos when I grow up," proof that inspiration often strikes when complex ideas are wrapped in wonder. Documentaries played a pivotal role too. Films like Neutrino, the ghost particle, wove archival footage of IceCube's construction with animations of the Blazar's jet, turning theoretical physics into a cinematic adventure. The key was framing scientists not as distant geniuses but as persistent detectives. Viewers saw researchers celebrating eureka moments, yes, but also enduring Antarctic storms, debugging faulty sensors, and poring over false alarms for years. That authenticity resonated. A physics professor in Toronto recalled a surge in students declaring astrophysics majors after the film aired, citing its portrayal of science as a marathon of curiosity. Universities took note, launching outreach programs that brought neutrino research to underserved communities. In Chile, astronomers partnered with rural schools to build simple cloud chambers from dry ice and alcohol, letting students track cosmic rays, neutrinos' bulkier cousins. In South Africa, a mobile planetarium tour used the Blazar story to explain how African-led projects like the upcoming KM3 NET telescope would expand the global search. These initiatives did more than teach, they democratized access, proving you didn't need a lab coat to contribute to cutting-edge science. One teenager in Nairobi later credited a workshop with sparking her ambition to study particle physics. They showed us how a discovery in Antarctica could start with a question from someone like me. The ripple effects reached beyond STEM. Art students painted neutrino trails as celestial brushstrokes. Musicians composed symphonies based on IceCube's data sonifications. A Pulitzer finalist poet even wrote a cycle comparing neutrinos to letters from a war we never saw, written in ink that vanishes as you read. This cross-pollination of science and culture reinforced a powerful idea that the universe's mysteries belong to everyone. When the Blazar neutrino made headlines, it wasn't just a breakthrough for astrophysicists, it was a shared moment of awe, a reminder that curiosity transcends disciplines. Perhaps the most enduring impact lies in the stories we haven't heard yet, the students who'll one day trace their careers back to a museum visit, a documentary scene, or a teacher's lesson about a particle that bridged 4 billion light years. The neutrino didn't just change how we see the cosmos, it lit a path for those who'll see further. And somewhere, right now, a future scientist might be staring at a starry sky, wondering what other ghosts are out there waiting to be caught. The moment we trace a neutrino back to a distant blazar or decode the secrets of a black hole's jet, we're not just observers, we're participants in a cosmic conversation. And with that role comes responsibility. Consider the implications of studying events so far away, their light reaching us billions of years after they occurred. Are we merely chroniclers of the past, or does our ability to detect these phenomena somehow alter their significance? The blazar that fired that neutrino didn't know it would be caught. But now that it has, its violence is forever part of human knowledge, shaping how we understand the universe. This raises a subtle but profound question. Does observation at such vast distances carry ethical weight, or are we overstating our impact on events that unfolded long before Earth existed? Then there's the darker side of cosmic exploration, the potential for unintended consequences. While we're not yet capable of influencing distant galaxies, our tools are growing more powerful. Future neutrino detectors might be sensitive enough to pick up signals from civilizations, should any exist. How would we handle the discovery of artificial neutrino patterns deliberately sent across the void? The protocols for such a scenario are murky at best, tangled in debates about whether humanity should respond, or if broadcasting our presence might invite risks we can't foresee. Even without extraterrestrial contact, there's the matter of resource allocation. Building observatories like IceCube or KM3 requires massive funding money that could, in theory, address urgent problems like poverty or climate change. Defenders argue that fundamental research has historically sparked unforeseen innovations, from medical imaging to GPS, but critics counter that the immediate needs of Earth's population should take precedence over probing distant black holes. Perhaps the most overlooked ethical dimension is cultural. The skies have always been a canvas for human stories, from ancient constellations to modern astrophotography. When science redefines celestial phenomena like recasting a demon star's flicker as a Blazar's jet, it reshapes cultural narratives built over millennia. Indigenous astronomies, for instance, often weave cosmic events into creation myths and moral teachings. How do we balance the pursuit of empirical truth with respect for these traditions? Some telescopes now incorporate dual naming systems, acknowledging both scientific designations and indigenous labels, but the tension between knowledge systems remains unresolved. At its core, the ethics of space research forces us to confront humility. The Blazars neutrino was a reminder that we're latecomers to a universe that's been unfolding for billions of years. Our detectors, however advanced, are still catching whispers from events we had no part in and likely never will. That humility might be the greatest ethical guidepost of all, the recognition that some mysteries aren't ours to solve, but simply to witness with awe. And as we peer deeper into the cosmos, that perspective could be the key to exploring not just responsibly, but reverently. The same cutting-edge technology that allows us to catch ghostly neutrinos from distant galaxies is quietly transforming lives here on Earth. It turns out that building sensors sensitive enough to detect particles that barely interact with matter has led to breakthroughs far beyond astronomy, revolutionizing everything from cancer treatment to global security. Take medical imaging, for example. The photomultiplier tubes developed for IceCube, capable of spotting single photons in the pitch-black depths of Antarctic ice, are now being adapted for next-generation PET scanners. These devices can trace the spread of diseases at a cellular level, helping doctors pinpoint tumors with unprecedented precision. Similarly, algorithms created to filter neutrino signals from background noise are now used to enhance MRI scans, teasing out subtle abnormalities that older machines might miss. Then there's nuclear monitoring. Neutrino detectors were originally designed to study cosmic events, but their ability to sense certain particle interactions makes them ideal for spotting clandestine nuclear activity. Some next-generation detectors can identify the unique neutrino signatures of nuclear reactors, acting as invisible watchdogs that verify compliance with international treaties. Unlike traditional monitoring methods, which can be blocked or deceived, neutrino-based systems offer a nearly foolproof way to track nuclear fuel processing, an innovation that could reshape global security. Even more remarkably, scientists are exploring whether similar technology could detect nuclear waste stored underground, reducing the risk of environmental contamination. The ripple effects extend to environmental science too. Techniques developed to distinguish atmospheric neutrinos from cosmic ones are now helping climatologists analyze data from deep sea sensors, improving models of ocean currents and temperature shifts. Meanwhile, the ultra-pure materials created to minimize interference in neutrino experiments have found unexpected uses in semiconductor manufacturing, leading to faster, more efficient computer chips. It's a pattern as old as science itself. The tools we build to answer abstract questions often unlock solutions to problems we hadn't even considered. Perhaps the most poetic spin-off lies in archaeology. Neutrino detectors rely on shielding materials to block stray particles, a challenge that led to advances in ultra-sensitive radiation shielding. These same materials are now used to protect delicate artifacts during radiocarbon dating, allowing historians to pinpoint the age of ancient objects without damaging them. From the depths of space to the ruins of lost civilizations, the same technology bridges seemingly unrelated worlds. What makes these innovations so extraordinary isn't just their diversity, it's how accidental they were. No one set out to improve cancer diagnostics or nuclear safeguards when designing IceCube. Those breakthroughs emerged organically from the pursuit of pure knowledge. And that's the real lesson here. Fundamental research isn't a luxury. It's a wellspring of practical solutions waiting to be discovered. Every time we push the boundaries of what we know, we're not just exploring the cosmos, we're planting seeds for technologies that might one day change lives in ways we can't yet imagine. For all the brilliance of tracing a single neutrino back to a cataclysmic explosion 4 billion light-years away, the discovery laid bare an uncomfortable truth. We've barely scratched the surface of the cosmos's secrets. Think of it like stumbling upon a single page from an epic novel, thrilling, yes, but also a humbling reminder of how much story remains untold. That neutrino didn't just solve a mystery, it exposed gaping holes in our understanding of particle physics, black hole dynamics, and the very fabric of space-time. Consider this, we now know blazars can produce high-energy neutrinos, but we have no idea how often this happens, or why some flares launch particles while others don't. The universe operates on scales and timespans so vast, our detectors are like eavesdropping on a conversation where we catch one word every century. Even IceCube, with its cubic kilometer of ice, misses more neutrinos than it catches. And what about the ones that slip through? They might carry clues to phenomena we haven't even imagined yet: cosmic strings, quantum foam, or dark matter interactions whispering just beyond the edge of our perception. This isn't just about incomplete data, it's about fundamental limits. Light has a speed, telescopes have resolutions, and human brains evolved to comprehend a world of medium-sized objects moving at medium speeds. The universe doesn't care about those constraints. It flings particles with energies a billion times beyond our colliders, warps space-time into knots, and hides 95% of its mass in shadows we can't see. Try explaining quantum entanglement or black hole singularities using everyday logic, and you'll hit a wall, not because the ideas are complex, but because reality itself operates on rules that defy intuition. Yet here's the paradox: every time we hit one of these walls, we find a way to climb. When Isaac Newton's laws broke down at cosmic scales, Einstein gave us relativity. When relativity clashed with quantum mechanics, string theory emerged. The Blazar neutrino is another foothold in that endless ascent. It proved that multi-messenger astronomy works, that we can combine light, particles, and even gravitational waves to see further than ever before. But it also revealed how much we've been missing. For centuries, astronomy was like studying a forest by only looking at the trees. Now we've learned to listen for the rustle of leaves, the snap of twigs, the scent of soil after rain, and it turns out the forest is infinitely richer than we'd guessed. The real lesson here isn't just humility, it's possibility. The gaps in our knowledge aren't failures, they're invitations. Every unanswered question about that neutrino, why it arrived alone, how it survived the Blazar's chaos, what its energy reveals about particle acceleration, is a door waiting to be kicked open. And behind each door, not just answers, but new questions waiting to unravel everything we thought we knew. That's the heartbeat of science, not the satisfaction of solving puzzles, but the thrill of finding bigger, stranger ones. The universe isn't a mystery to be cracked, it's a conversation that never ends. And with each detection, we're not just listening, we're learning how to reply. Scientists have turned this single neutrino detection into a cosmic Rosetta Stone, a key to deciphering how the universe's most violent events speak to us across different wavelengths and particles. By stacking it alongside other extreme phenomena like gamma-ray bursts and gravitational waves, they're assembling a multilingual dictionary of cosmic catastrophe. Take gamma-ray bursts, for example. These fleeting flashes of high-energy light, often linked to collapsing stars or colliding neutron stars, pack more energy in seconds than our sun will emit in its entire lifetime. When telescopes caught a gamma-ray burst from a neutron star merger in 2017, it wasn't just the light that told the story. Gravitational waves rippled through detectors at the same time, confirming the event's colossal scale. Now, with neutrinos in the mix, we've added another dialect to this cosmic language. The parallels are striking. Just as gravitational waves reveal the choreography of massive objects warping space-time, and gamma rays expose the fury of particle acceleration, neutrinos offer a backstage pass to the particle collisions themselves. Imagine witnessing a volcanic eruption. Gravitational waves would capture the mountain's shudder, gamma rays the incandescent lava, but neutrinos, they'd let you taste the chemistry of the molten rock, revealing elements forged in the explosion's heart. That's the power of multi-messenger astronomy. It doesn't just show us the universe's fireworks, it dissects the gunpowder. Yet the differences between these cosmic messengers are as revealing as their similarities. Gamma rays travel at light speed but can be absorbed or scattered by interstellar dust, like headlights dimmed by fog. Gravitational waves, while pristine, only betray the motion of massive objects, silent on the particle chaos within. Neutrinos, by contrast, slice through everything, carrying unfiltered details about the environments that birthed them. When scientists compared the Blazar's neutrino to gamma-ray data, they noticed something peculiar. The jet's gamma-ray flare peaked weeks before the neutrino arrived. That delay hints at separate acceleration mechanisms within the jet, like hearing an echo long after the shout, suggesting unseen chambers in a vast cave system. These comparisons are rewriting astrophysics textbooks. Before multi-messenger observations, theorists treated phenomena like gamma-ray bursts and Blazar flares as distinct categories. Now they're searching for a unified framework, a grand unified theory of cosmic violence that explains how black holes, neutron stars, and other extreme objects channel energy into particles, light, and ripples in spacetime. Some models suggest that the same magnetic reconnection processes that power solar flares might scale up to drive Blazar jets, while others propose that neutrino production requires shock waves akin to those in supernova remnants. Every new detection, whether of neutrinos, gamma rays, or gravitational waves, is another piece of the puzzle, forcing theorists to redraw their diagrams. But the biggest surprise, how often these events defy expectations. When the LIGO and Virgo detectors spotted gravitational waves from a neutron star collision, many assumed it would produce a neutrino burst. None arrived. Conversely, the Blazars neutrino came without accompanying gravitational waves. These mismatches aren't failures, they're clues. They tell us that the universe's particle accelerators don't follow a single blueprint. Some events, like colliding neutron stars, might shunt energy into gravitational waves and light but skip neutrino production. Others, like flaring blazars, could prioritize particle acceleration over space-time ripples. It's as if the cosmos has multiple genres of catastrophe, each with its own signature. What's emerging is a new kind of cosmic taxonomy, a classification system based not just on how events look, but on how they broadcast their stories across different messengers. A supernova might shine brightly in neutrinos but faintly in gamma rays. A magnetar's flare could light up radio telescopes while leaving neutrino detectors silent. By cross-referencing these signals, scientists are mapping the universe's disaster spectrum, from quiet fizzles to apocalyptic bangs. And with each new event added to the catalog, the picture grows richer, revealing patterns we'd never spot with just one type of observation. This isn't just academic curiosity. Understanding how cosmic violence distributes its energy into particles, light, or space-time ripples could unlock practical insights, from the nature of dark matter to the origins of cosmic rays that bombard Earth. It might even reshape our search for extraterrestrial life by identifying which cataclysms sterilize galaxies and which could forge the elements essential for biology. Every neutrino, gamma-ray burst, or gravitational wave detection is more than data. It's a stroke in a masterpiece we're only beginning to outline. And as our detectors grow more sensitive, the universe's most extreme events won't just be mysteries to solve, they'll be teachers, showing us the rules of a game we're only now learning to play. The blazar that fired off that solitary neutrino has become astronomy's newest obsession, not just for what it revealed, but for what it might still hide. Like a volcano that erupts once and then falls silent, scientists are left wondering, was this a freak event or the first rumble of something far more persistent? The answer could rewrite our understanding of how black holes channel their fury into the cosmos. Right now, telescopes and neutrino detectors are trained on that patch of Orion like never before, scanning for any hint of another high-energy particle making the 4-billion-year journey to Earth. But catching a repeat performance isn't just about patience, it's about untangling the blazar's rhythms. Some theories suggest these jets operate in cycles, with periods of quiet punctuated by violent outbursts as the black hole devours clumps of matter. If that's true, the neutrino might have been a single note in a much longer symphony, with the next movement already queued up. Other models propose that neutrino production requires freak conditions, a perfect storm of magnetic field alignment and particle density that might not recur for centuries. The stakes are higher than they seem. If this blazar fires off another neutrino, it would confirm that these jets aren't just cosmic one-hit wonders, but steady producers of high-energy particles. That would make them prime suspects in one of astrophysics' longest-standing mysteries, the origin of ultra-high-energy cosmic rays, particles that streak through space with energies 1,000,000 times beyond anything our most powerful colliders can create. We've known for decades that something out there is accelerating particles to these insane speeds, but pinning down the source has been like trying to find a fingerprint on a bullet fired from a sniper rifle miles away. A second neutrino from the same blazar would be as close to a smoking gun as we've ever gotten. Yet absence could be just as revealing. If years pass without another detection, it might mean these events are vanishingly rare, flukes that occur when a black hole's jet hiccups in just the right way. That would force scientists to reconsider how particles reach such extreme energies, potentially pointing to entirely new mechanisms hidden in the chaos of these jets. There's even a tantalizing third option, that neutrinos arrive in clusters too faint for current detectors to spot reliably, like hearing only every 10th word of a whispered conversation. Next-generation observatories like KM3NT, with their vastly improved sensitivity, could finally catch these murmurs, revealing patterns we're currently blind to. What makes this wait so electrifying is how it mirrors other breakthroughs in astronomy. When the first fast radio burst was detected in 2007, it took years of searching before a second one appeared, proving they weren't glitches but a genuine cosmic phenomenon. The same could be true here. Every moment that passes without another neutrino tightens the suspense, sharpening the question, are we witnessing a cosmic anomaly or the first glimpse of a universal process? The answer won't just tell us about one blazar, it'll reveal how the universe's most powerful engines distribute their energy, and whether Earth's detectors are tuned to their rhythm or just catching static from the void. Until then, the hunt continues, a testament to science's most thrilling axiom. Sometimes the most profound discoveries begin with a single, inexplicable signal, and the stubborn refusal to let it remain unexplained. Neutrinos might be the universe's ultimate time capsules, tiny, nearly massless particles that could carry whispers from the very birth of everything. While we've traced some to distant black holes and exploding stars, the most tantalizing possibility lies even further back, the Big Bang itself. Theoretical models suggest that in the first searing seconds after the universe's birth, neutrinos were forged in such staggering numbers that a remnant background of them should still permeate space today, much like the cosmic microwave background radiation. But unlike light, which was trapped in the hot, dense early universe until it cooled, neutrinos slipped free almost immediately, untouched by the chaos around them. If we could detect these primordial neutrinos, they'd offer a snapshot of the cosmos just 1 second old, a window into conditions even the oldest light can't reveal. The challenge, of course, is finding them. These relic neutrinos would have cooled over billions of years, their energy diluted by the expanding universe to a faint whisper, just a fraction of a degree above absolute zero. Current detectors like IceCube are tuned for high-energy neutrinos from cataclysmic events, not these ancient, icy ghosts. Catching them would require technology sensitive enough to spot a particle with less energy than a snowflake's touch. Yet the payoff would be staggering. Primordial neutrinos could confirm theories about how matter triumphed over antimatter in the early universe, or whether exotic particles like sterile neutrinos played a role in shaping cosmic structure. They might even carry traces of physics beyond the standard model, clues to forces or dimensions that vanished as the cosmos cooled. This isn't just pie-in-the-sky speculation. Scientists are already designing next-generation experiments to hunt for these relics. Projects like Ptolemy aim to trap neutrinos on solid-state detectors chilled to near zero temperatures, while others explore using quantum sensors to pick up their infinitesimal vibrations. The techniques border on science fiction, but the principle is grounded in decades of particle physics. After all, we once thought detecting any neutrino was impossible until a tank of dry, cleaner fluid buried in a South Dakota mine proved otherwise in the 1960s. If history's any guide, what seems unthinkable today might be tomorrow's breakthrough. What makes this search so compelling isn't just the science, it's the sheer audacity of the quest. We're talking about particles that have traveled uninterrupted since the universe's first breaths, outlasting galaxies, stars, and planets. They've witnessed every epoch of cosmic history, from inflation to the formation of the first atoms, and they've done it all without interacting with anything. In a way, they're the perfect messengers, silent, steadfast, and unchanged. If we ever learned to read their signals, it would be like uncovering a lost diary from the dawn of time, one written in a language we're only beginning to decipher. For now, the hunt remains a tantalizing what if. But with each advance in detector technology, we get closer to answering one of cosmology's biggest questions. Can we reach far enough back to touch the moment everything began? Whether the answer is yes or no, the pursuit itself reminds us why we peer into the void, not just to map the universe, but to understand our place within its unfolding story. And somewhere in that vast expanse, a neutrino from the Big Bang might already be on its way, carrying secrets older than time itself. Buried beneath mountains of data from neutrino detectors lies a challenge straight out of a cosmic detective novel: how to spot the faintest whisper of a particle in an ocean of noise. That's where artificial intelligence steps in, not as a replacement for human intuition, but as a force multiplier for scientific discovery. Modern neutrino observatories like IceCube generate petabytes of raw data annually, equivalent to streaming every movie ever made in ultra-high definition twice. Sifting through this avalanche manually would be like searching for a single misprinted letter in the Library of Congress. AI changes the game by learning to recognize the subtlest signatures of neutrino interactions, distinguishing them from cosmic ray showers, sensor glitches, and even the occasional curious penguin-tripping detectors near the South Pole. The magic lies in machine learning algorithms trained on simulated neutrino events. These digital apprentices study millions of synthetic collisions, learning to identify patterns no human eye could discern. For instance, when a neutrino strikes an atomic nucleus in IceCube's ice, it creates a cone of blue Cherenkov light that sensors capture as a waveform. Traditional analysis might miss events where the light scatters unpredictably, but AI can reconstruct these messy signals with shocking precision, like listening to a symphony played through static and still identifying every instrument. Recent breakthroughs show neural networks pinpointing neutrino directions with half the error margin of conventional methods, turning fuzzy trajectories into laser-sharp backtracks to their cosmic origins. But AI's role extends far beyond pattern recognition. At facilities like the upcoming cubic kilometer neutrino telescope, machine learning optimizes real-time operations, deciding which neutrino candidates warrant immediate telescope follow-ups within seconds of detection. This instant triage prevents missed opportunities when Earth rotation carries a potential source below the horizon. Some systems even predict optimal observation schedules, accounting for variables like moonlight interference or competing research priorities across global telescope networks. It's as if the detectors have gained a sixth sense, an anticipatory awareness of where and when to look next. Perhaps most remarkably, AI is uncovering anomalies that defy existing theories. In 2022, a machine learning model analyzing years of IceCube data flagged a cluster of neutrinos with eerily similar energy profiles but no obvious source. Follow-up studies revealed these particles might originate from a previously unnoticed class of quiet Blazars galaxies, whose jets emit neutrinos without the telltale gamma-ray flares scientists expected. This discovery, driven by algorithms spotting connections humans overlooked, suggests entire populations of neutrino factories might be hiding in plain sight. A collaboration between human and machine intelligence is rewriting the playbook for cosmic exploration. While AI crunches data at inhuman scales, researchers focus on interpreting results, designing new experiments, and crucially, asking better questions. Like a telescope that extends our vision, artificial intelligence amplifies our ability to decode the universe's secrets, one neutrino at a time. And as these tools grow more sophisticated, they're not just assisting science, they're helping redefine what's possible in our quest to understand the cosmos. The discovery of a single neutrino tracing back to a distant blazar doesn't just expand our scientific horizons, it rattles the very foundations of how we perceive reality. We live our lives tethered to the tangible, trusting what we can see, touch, and measure. Yet here's a particle so elusive, it passes through our bodies by the trillions every second without a trace, carrying secrets from the far edges of existence. It's a humbling reminder that the universe operates on scales and principles far beyond human intuition, governed by forces we're only beginning to glimpse. This revelation forces a profound shift in perspective. For centuries, humanity placed itself at the center of the cosmos, interpreting reality through the narrow lens of our senses. But neutrinos defy that arrogance. They whisper that the vast majority of the universe's activity happens in realms invisible to us, not just distant in space, but hidden in plain sight. Think of it like this: if the cosmos were an iceberg, everything we perceive, stars, galaxies, even the black holes we see through their gravitational effects, is just the tip. The rest, the bulk of reality, is a silent, seething ocean of particles and interactions we've barely begun to map. What does this mean for our place in the universe? On one hand, it could feel isolating, a reminder of how small and fleeting we are against the backdrop of cosmic time. Yet there's another, more exhilarating interpretation. We're not just observers of this hidden drama, but participants. Every atom in our bodies was forged in stellar explosions, and now, with tools like IceCube, we've learned to catch echoes of those very processes. That neutrino didn't just travel 4 billion light-years to a detector. It bridged the gap between the unimaginably vast and the intimately human, linking us to events older than Earth itself. The philosophical implications run even deeper when we consider how much remains unknown. For all our advances, neutrinos are still full of mysteries: why they have mass, how they oscillate between flavors, whether they might hold clues to the asymmetry between matter and antimatter. Each unanswered question is a doorway challenging our assumptions about how reality works. Take the Blazars neutrino. Its solitary arrival defied expectations, hinting at gaps in our understanding of particle acceleration. It's as if the universe is teasing us, offering just enough to append our theories while withholding the full picture. This dance between knowledge and mystery is what makes science so vital, not just as a tool for answers, but as a lens for wonder. The neutrino's journey reminds us that the cosmos isn't a static backdrop to human existence. It's an active, evolving story we're only starting to read. And in that story, every detection, every anomaly is a chance to rethink what's possible. Whether we're philosophers or physicists, artists or engineers, that's an invitation worth embracing. To stay curious, stay humble, and keep reaching for the next great revelation, knowing it might come from the most unexpected of messengers. The story of this neutrino is more than just a scientific triumph. It's a shining example of humanity's relentless drive to uncover the universe's hidden truths. Think about the chain of events that had to align perfectly. A supermassive black hole 4 billion light-years away launches a jet of particles with unimaginable force. One neutrino slips through the chaos of intergalactic space, travels undisturbed for eons, then against all odds collides with a single atom in a detector buried deep beneath Antarctic ice. The chances of us catching it were astronomically small, yet here we are, rewriting textbooks because of that one in a quadrillion encounter. What makes this discovery so extraordinary isn't just the cosmic distance it bridged, but the human ingenuity that made it possible. Building IceCube was an act of breathtaking ambition, transforming a cubic kilometer of pristine ice into the world's most unlikely particle detector. Teams endured Antarctic blizzards, engineered sensors capable of spotting single photons in pitch darkness, and developed algorithms to sift meaning from mountains of noise. All this to catch particles that most would consider undetectable. That stubborn refusal to accept limits is science at its finest, taking what seems impossible and making it routine. Now consider the broader implications. Before this breakthrough, high-energy neutrinos were cosmic mysteries, arriving without return addresses. Today, they've become a new form of interstellar communication, carrying unfiltered news from the universe's most extreme environments. We're not just passive observers anymore. We're actively decoding messages from black holes, neutron stars, and who knows what else. And with next-generation detectors coming online, our ability to interpret these ghostly signals will only grow sharper. Imagine what we might learn when we can reliably trace neutrinos back to their sources, perhaps new laws of physics, hidden dimensions, or even entirely unknown cosmic phenomena. This story also reminds us that the universe loves surprises. For all our theories and models, nature keeps throwing curveballs like that lone neutrino arriving without the expected shower of companions. These anomalies aren't frustrations, they're invitations to dig deeper, to question our assumptions, and to stay humble in the face of the cosmos' complexity. Every time we think we've got things figured out, the universe winks and shows us another layer of its infinite puzzle. Looking ahead, one thing is certain: this is just the beginning. As detection methods improve and international collaborations expand, we're building a new cosmic network, one that listens not just with light, but with gravitational waves, neutrinos, and whatever other messengers the universe might be using. The next great discovery could come tomorrow, when a detector in the Mediterranean catches a neutrino from a colliding neutron star, or when an AI algorithm spots an anomaly in decades-old data. The only guarantee is that the universe still has countless stories left to tell, and neutrinos might just be the perfect translators. So while we celebrate this milestone, keep your eyes on the horizon. Because somewhere out there, another ghostly particle is streaking through the dark, carrying secrets we haven't even thought to ask about yet. And when it arrives, you can bet scientists will be ready, turning whispers from the void into revelations that change how we see everything. The cosmic detective story continues, and the best chapters are still unwritten.